we're going to get started by talking about some different file formats and different ways we can represent molecules just on the computer. And so we're going to start off pretty simply using line notations. Line notations use strings of characters, and we can represent molecules with these strings just by piecing them together. And so our probably most simple one we're going to look at is SMILES. SMILES is a simplified molecular input line entry system where we can represent atoms just with letters. So carbon is C, hydrogen's H, nitrogen's N. But we do have some rules we follow. We can represent single, double, triple bonds, or aromatic, or any bond. If we're working with capital letters, we're talking about aliphatic atoms. Aromatics are typically represented in lowercase. So we can have a hexane with this string of C's, but if we want a cyclohexane, we have to denote that this C1 is being joined by this 6th C over here back to C1. And so now we're creating a ring. And then same thing down here, C1 to C1, but we have a nitrogen in here, and this is also aromatic, so we're looking at pyridine. SMARTS is built up upon SMILES, so we're getting a little more complex. So there's a lot of things we can't represent with SMILES that SMARTS kind of builds upon, like stereochemistry. So we can now do some RNS enantiomers with SMARTS. We can now represent any atom with a wildcard. So let's say I have a big database of SMILES and I'm searching for this, let's say, nitrile group. So I can say any atom with this wildcard character, or A, or capital A, and then my C triple bond N. SMERCS uses both SMILES and SMARTS notations to represent molecular transformations. So if we're representing a reaction, we can go from a SMILES string of reactants to maybe an agent and then a product using just these arrows. And there's several software packages have used these SMERCS, and we can represent our molecules using these. We do have a couple problems with line notations. One being with these, so this picture up on the left is going to be a SMARTS representation of this molecule, and we can see that we can get our stereochemistry with this RNS enantiomers, but if I'm comparing these top and bottom ones, these are the same molecule, but I have different strings to represent them based on how this molecule is oriented. And so this is a problem. We don't really have a way of talking about these. One way is not better to describe these versus on the top and the bottom. And so that may be one problem coming across. Also, we can represent molecular fragments with SMILES and SMARTS with these periods over on the right. But if I want to get this nice ferrocene, unfortunately, if I type this in, what the computer is going to throw back at me is this ferrocene, just fragments, charged fragments that isn't so helpful if we're trying to build nice molecules. So to kind of get a little more complex, talking about different file types. Oops, there we go. Getting into XYZ, so now we're adding a 3D element. SMILES and SMARTS don't carry any sort of coordinate system, and so if we want to get a simple, just Cartesian coordinates out of our molecules, we can use XYZ file formats. And these formats are specified, just we tell it the number of atoms. You can add a comment line. If you don't add a comment on this line, such as like the name of the molecule, people typically do that. You can just leave it blank, and then you'll start off with your element. So just the symbol. So this would be like a carbon, hydrogen, nitrogen, and then it's XYZ Cartesian coordinates, and you follow that until you've reached the number of atoms that you specified. A little more complex, building upon that, is our structured data format, an SDF file. This holds, so in our mol block, we'll hold our Cartesian coordinates, some information about connectivity of our atoms, but then we can also specify structural information or properties as well below the mol block. So we can put something in there like molecular weight, maybe the energy. These you can define yourself, so it doesn't really matter what kind of properties you want those to store. It's kind of handy if you want them to store information like this. Talking about now data interchange formats. This JSON JavaScript object notation is really quite simple to read. It's very human readable, and it's easy for machines to go through and look for something like the name, what's the formula, what are the coordinates. People use these, PubChem uses these to export molecules, and it's easy for quick searching. And you can also store, much like the SDF files, properties. So we can say how many bonds, what's the connectivity of these bonds. Maybe if this was coming from a calculation, what program did we use? What is our basis set? What's our level of theory? And stuff like that. Basically any property you want to store at the end of these files. So in converting from one file type to the next, we use a nifty tool called OpenBable. It's our Babelfish translator, going from any file type, well, not any. A lot of they do have a lot of file types, and we can convert those from one to another. We can use this on the terminal. They also have a Python and C++ API. Those are really handy for us. But how we specify these on the terminal is using these options, so we can give it an input file type, output file type, and then a file type name, or a file name. If we're trying to generate 3D coordinates, OpenBable can do that for us using an MMFF94 force field. This is just kind of an example of converting this tert-butyl around. So if I start with this SDF file, I'm going to give it my SDF, and I want an output of an XYZ. Maybe I want something simpler to work with. So I go from my XYZ down to just a smile string, and OpenBable will give me my smile string just in a file that I specified. But if I want to go from my smile string to something with 3D coordinates, remember our smile strings don't carry any information on the coordinates of our molecule. I'm going to use my Gen3D, my MMFF, just to give me a rough estimate of what this molecule is going to look like, and then maybe I can do some more hardcore optimizations of that to get something like what we'd see, maybe run some quantum calculations from there. So up next, we use basically a combination of all these tools with RDKit. RDKit is the Rational Discovery Toolkit. It started development in 2000 by this company called Rational Discovery, which is no longer a thing. But in 2006, Greg Landrum, who was working at Rational Discovery, published this using an open source BSD license, and now we have a lot of developers. It's a huge project, really collaborative, and really great for transforming and working with molecules. They have APIs in Python, C++, Java, and KNIME, which makes it handy to kind of use whatever system we want to build. But it's really handy with cheminformatics applications. We can use fingerprinting to do some similarity searching. We can substructure search. We can replace certain substructures with molecules. It makes it easy to transform and manipulate molecules. We use it also to do rough optimizations of molecules, which I'll talk about on this slide. So how we have been using RDKit lately is we can use RDKit to find all of our torsion angles in our molecule, rotate the molecule around those torsion angles, just to generate a bunch of conformers at different angles. And then we can do some low-level force field optimizations using MMFF or UFF. And then we can do some higher-level semi-empirical optimizations. Still, this is just all in RDKit in Python. And then maybe we check how many duplicates we have, and then with the remaining conformers, we'll send those to maybe a quantum calculation, do some DFT on those. So this is kind of just some pseudocode on what one of our programs does with these molecules. So I'll generate a molecule from a smile string. So I'll give my program maybe a text file with a bunch of smile string. we'll generate this mole object, which RDKit recognizes as a molecule. And then I'll use, in this case, I'm using the UFF force field, so the universal force field, to minimize that structure. And then I can use something, we use another tool called the Atomic Simulation Environment, ASE, which allows us to do some semi-empirical optimizations, which I'll talk about on the next couple slides, just about what kinds of semi-empirical or neural net trained optimizations we do. So one of these are kind of what we use for our more higher optimization. The first one is going to be ANI1. This is Accurate Neural Network Engine for Molecular Energies, Anakin, or ANI1 for short. They are really stretching that title, but they have trained, this is actually a neural net trained model against hydrogen, carbon, nitrogen, and oxygen. It's trained against DFT calculations, and so the energies that we'll get if we're using these atoms should be close to DFT optimized energies. Unfortunately, since it was only trained against hydrogen, carbon, nitrogen, and oxygen, we can only use those atoms to optimize our molecules. We can only use molecules that contain only those atoms, otherwise we'll get, it actually won't let you optimize. The next semi-empirical optimization is XTB. This is from Stefan Grimme. They recently released their source code on GitHub. And so what we've been using is they have kind of a weird Python API so far. It doesn't do everything as just their standalone XTB program does, but it does allow us to do GFN2 XTB, which GFN2 is geometries, vibrational frequencies, non-covalent interactions, using this XTB, or this tight binding optimization, which is similar. It makes it really fast. It's a pretty good optimization, but it cuts some corners compared to DFT. So it's not perfect, but it does give you really nice structures. So close to what we would see in an optimized DFT. Output.
Does that do all elements, or is it also limited?
Yes. So that's our benefit of using GFN2. We can use all elements on the periodic table. If we use the universal force field beforehand, which also works with all elements, those are both bonuses of using GFN2 XTB. So yeah, up next, Lily's going to talk about some other kinds of workflows and charts that we use.
Yeah, so I'll give a brief summary of some of these methods that they're to do conformational searches. So this one is a combination of quantum mediated molecular mechanics with CAT-BS. And so basically you can input a smile string or draw up your structure, and so it will apply to this template with this predefined library, ligand library. It will merge these structures using your selected force field, and then based on the force field, it will optimize the parameters to apply to these electronic structures, which will do this conformational search and then output these Boltzmann averaged conformations. And so the good thing about this is that it can do transition state force fields very rapidly, and it can calculate the stereoselectivity of the organic reactions. And so, in this other review, comparing these force fields, they compared to determine the accuracy and the reliability of these force fields for conformational searching. And this table here shows you all the force fields they used. And so basically they found that the MFFF94 and PM97 were at least closest to the DFT conformational searches. And so they found that 6% of the conformers were using MFFF were the lowest energy were within 1 kcal, and then within 10 kcals were the 70% of the conformers generated. However, using PM7, they had better conformer searches of the lowest energy within 1 kcal per mole, and then the rest, 91%, within 10 kcals. So from this study, they also looked at using force fields as an initial screening, and they found that the MFF94, however, doesn't, in comparison to PM7, it still ranged between 50 to 140 kcals per angstrom for its conformational. So in conclusion, they found that these force fields do not produce the energy surface current in comparison to PM7. So yeah. And then, so some of these toolkits that Julian was talking about was included RDKit. And so in this review, they have a comparison between the toolkits of Balloon, Confab, and Frog2. And they did 3 different studies of one of accuracy of how close the generated conformer compared to the experimental results. And so they found that using RDKit uses this stochastic approach, and it performed the best for rotatable bonds between 0 and 10, and 0 and 9, and then anything greater than 10 rotatable bonds, Confab performed the best, and which uses a systematic approach. And then the next thing they tested for is to see how diverse these conformers are being generated. And in comparison to all of them, RDKit had most of its structures very similar. So in order to avoid this problem, they did a post analysis, a method to filter out any of these similar compounds by doing comparing the RMSD values of the energies of these conformers. And so, okay. And then the last thing was how much of the computational time does it take to generate these conformers? And then this chart down here shows that Frog2 is the fastest in comparison to any of the other ones, but RDKit was also pretty fast. So in overview, they pretty much claim that RDKit is pretty much a good approach, a good toolkit for this conformational search. Okay. So.
Right. Oh. We were thinking, do we have a lot of time left for our part?
What?
Do we have, if we have a couple minutes, we're going to do a little demo for.
Sure. I think. Yeah, you used less than 20 minutes, so
cool.
You want to go through a few things.
Yeah. Let me just share. Oh, there we go. Okay. So I was just going to kind of walk through. We have a script that kind of does this workflow of going from a smile string to generating conformers with RDKit. So I was just going to kind of show one way that we do that. So I'm going to start with ChemDraw. And what should I do? Let's say I have this cyclohexane and it's going to be branched. Oops. And we'll throw, what atom should I throw on there? A fluorine over here. And so what I'm going to do is select this molecule and then copy it as a smile string. So now I have the smile string of this molecule. I can paste that out. And using one of our computers that has this, our programs on it, I'm going to paste that molecule in, give it a little name, save that guy. And now I'm going to run, we have a script called RDConf. I'm going to tell it to optimize with XTB. I'm also going to give it, tell it to rotate around our dihedrals.
So are you doing a screen share so we can see what you're doing? I'm not sure.
Can you not see? Sorry. Yes, I'm doing a screen share.
All right, now we can see. Thank you.
So I'm going to call my script RDConf. Using this text file contains my smile string. I'm going to do an XTB optimization. Let's also call, I want to use the UFF force field. And then I'm going to rotate around my dihedrals by 60 degrees. It's going to find all those dihedrals, rotate each of those, generate a bunch of conformers, and then optimize those conformers. And so, oops, let me actually cancel that. I want it to be those. So it found us 720 total conformers, and now that might be a lot for now. We found 20 unique conformers, and so we're going to go through those 20 conformers, optimize those, and then check have any of those conformers optimized to maybe the same structure based on their RMS and their energy. And so we'll go through those basically one at a time. This can take a while depending on the methodology we're using.
So Guilian, so just to sort of like interject.
Yeah.
So the 20 unique conformers that you get at the beginning, that's from the RDKit sort of stochastic embedding algorithm, right?
Mm-hmm.
And then the systematic generation is you're taking the side chain of that molecule and doing sort of a systematic rotation of all of those rotatable bonds, which is sort of why you're getting that multiple of 720, right?
Yes.
And
So,
UFF
so just as a
sorry.
So as an interesting paper, there's an infamous or famous paper from the mid-90s. Rob probably knows which one I'm referring to, with like Sanders and Schleier and Haug, that was associated with a very expensive restaurant bill because Ken lost a bet there. But that would be interesting to let that loose. I think they did.
So this is like Monte Carlo versus systematic, right?
Well, they used all kinds of different things.
Yeah.
Everybody had their own favorite method, and I forgot what molecule they used. C17, I think. Heptadecane, cycloheptadecane. I think it was. I'm not 100% sure anymore. But they let like a half a dozen different methods loose on that.
Right.
It would be interesting to see how that one compares to that.
Yeah, so I guess kind of in a nutshell, there's the choice of the level of theory, which, so essentially the sort of the engine that you use to get the energies, and then there's obviously the algorithm as well. We know that UFF is terrible. UFF is universal, which is brilliant. It always gives you a number. But generally speaking, things that always give you a number, that should be a bit of a warning flag. So the accuracy of UFF is pretty low. But you can use MMFF, which is preferable, but obviously Lily showed that review from Greg Hutchinson that sort of is, I think they titled that review like a sobering assessment of the quality of conformational energetics from force fields. So there are some, we know that that's also, you know, obviously not great, and depending on the system, it can be pretty awful. So really, I guess the ability to add other energy calculations. So here Julian's put XTB, could be a help. Again, ANI1 is also looks quite good for small organics with CHN and O. The systematic search Lily showed it works better when you've got more than 10 rotatable bonds, apparently, according to that review. But it's obviously very painful. 10 dihedrals with spacing of 60 degrees is going to give you, what's that, like 6 to the power 10 structures, which is huge. Is it still running?
Yep. Yeah, we're still going. We're on Conformer 57. So I don't know if we'll finish by the time we have to sign off, but
do you have an example SDF output file?
I do have an example SDF.
The other question would be on whether any of these things are the scripts and everything, whether it could be made available onto the CCAS team.
Yeah. Like it's yeah, absolutely. I mean, I'm sure that several of us have kind of things that do this already. Absolutely. I think that what are you showing?
So this is, okay, one of my outputs is going to be, it outputs in an SDF file. It'll throw all of the minimized conformers in those files. So if I look at this ST9, I can see that I have my Cartesian data and then my energy. This one was a bad example because there's only one conformer. But let me grab.
Julian, question. You know how you didn't assign the stereochemistry of that fluorine, right?
Yeah.
What does RDKit choose as like default stereochemistry?
Oh, I'm not actually sure what it chooses. It has to probably have a rule for.
I mean, your molecule, it doesn't matter because it doesn't have any diastereomers, but in principle it could.
True. I can look into that. I don't actually know. But this is, so let's see. This is a molecule, an SDF file that I have from one of those optimizations using that script. What we found was 5 conformers in this case, using those rotatable bonds, and then optimizing those individually. We basically just rotate this guy around a few times, and different conformers, different energies, and then we take these and submit those to Gaussian for some DFT optimization. Let's see how far along this guy is.
What do you want to say?
Yeah, so it's assigning a lot of these conformers. We get, out of those 720, we get a lot of duplicates, just based on, I think that's based on the RMS and the UFF energy.
Yeah,
You can hear from my laptop.
But yeah, does anyone have any questions other than on any file formats?
Well, I think we probably should move on, but I think Jess and Kevin are probably going to follow up on this with some of the things in Macromodel and some of the other tools and what to watch out for there next time. But I do want to get a second presentation in today.
All right.
So thanks, guys.
Yep.